I'm Michael Costello, speaking on behalf of the program committee, and I'm here to tell you about what took place at the most recent NANOG Hackathon. This is actually the 11th NANOG Hackathon, but the very first one that we've conducted all virtually. Participants worked all weekend, both Saturday and Sunday, on a variety of projects of their choosing. And we had participants ranging from across the United States, as well as from Canada and South Africa. The reason that we have the NANOG Hackathon is in support of NANOG's educational mission. We aim to share knowledge and to develop the next generation of networking professionals. It's organized by the program committee and takes place the weekend before the general conference. Participants work individually or self-organize into groups, and they work on projects of their own choosing. We had a variety of projects this time around. We had a from scratch BGP daemon. Another team did a performance monitoring and notifications using home control systems, while another group worked on simulating traffic and visualize it with streaming telemetry data. Earlier in the week, you saw a presentation on GNMI Gateway, and the author of that took the time over the weekend to develop a Kafka exporter and a netbox target loader for it. And finally, another person worked on a modern NetNews client library in Rust. We're not going to be giving presentations on those topics today. Instead, we're going to focus on doing RIB compliance using model-driven telemetry. Another group worked on a fully automated data center proof of concept. And finally, we have a last project that we're going to go over on a simple, automated, and easy to deploy SDN solution.
So thanks, Mike. Yeah, my name is Lawrence Bird. On the screen, you can see I was part of a team of 4. We're all network engineers from a company called Schlumberger. And the project we looked at was BGP RIB compliance using MDT, or model-driven telemetry. So really, the goal of our project was to evaluate various different technology stacks. We wanted to use this as an opportunity to look at some of the newer technologies out there for managing and administering networks. And so we looked at various different technology stacks, which you'll see in the presentation. We also wanted to look at specifically the capabilities of network telemetry and how we can use that in a real-time kind of evaluation scenario, as opposed to the traditional push-pull type of situations we have with things like SNMP. So in order to achieve that, we developed a network which was capable of showcasing various different routing scenarios. And the main ones we wanted to try and detect were poorly configured route maps, incorrect provider policies, such as MPLS providers and things like that, and then see if we could try and simulate and detect route hijacking, BGP route hijacking. So in order to achieve this, we use the following technology stack. So the devices that we were configuring, maintaining, were all based on Cisco. So we used the CSR 1000B, if anyone's familiar with that, which is one of the latest products that Cisco offer. And we use Cisco's modeling labs as our virtualization environment to build and deploy our network. We use Docker as a service provisioning and service chaining for the actual tooling that would be built on top of it and do the evaluation. And we use the Influx suite of tools, if you like, so InfluxDB, Telegraph, and Chronograph, to provide us with the real-time metrics and storage of that telemetry. And then finally, we use Python to do all of the policy processing, do the notification handling, and we began, it wasn't part of the project, but we began to create a WebSocket manager for that as well, so other consumers could subscribe to that information and use it as they see fit. So just quickly, let's have a look at the lab setup. I'm not going to go into detail of how the network was deployed, but on the right-hand side of the screen, you can see the overall kind of architecture of it. And what we wanted to do was simulate both an internal corporate network, which you see towards the bottom of the screen with, a virtualized or emulated MPLS network and various hub and spoke type scenarios. And then also connecting that out to a regional ISP and a third-party provider, and seeing if we can introduce a hacker in there somewhere to do some BGP hijacking. So as a reminder, the challenges that we were trying to overcome with this specific topology were to validate if the regional route preferences we have were being honored, specifically in this case for the default route. So the default route in Europe should go via the European data center versus in America, it should go via the America one. So can we validate that that's happening? And secondly, is traffic to or from our providers, in this case, the example here is Microsoft, being hijacked at any point? So this is the network topology, and as I mentioned, this is built in Cisco modeling labs. In terms of data collection, how did we do that? We had a simple Python script that would connect out to our devices that we identified in the YAML file, and using RESTconf with a render Ginger template, we would push down the telemetry config, which would basically allow the device to start streaming BGP events to our telegraph collector. So that was the first part of the setup, and this gets triggered when we bring up the Docker environment. So this script runs, we have our inventory file, and all of the devices will be configured with the appropriate exporter, shall we say. Then in terms of policy evaluation, we wanted to make this more of a framework than something very specific, right? So we were looking at trying to detect certain events, but really what we wanted to do is build something that could be reused in various different scenarios. So on the left-hand side here, using YAML, just because it was easy and we could do that in the time frame we had, we built a sample policy of what we might want to look at. So firstly, under regions, we're able to split devices up into regions, which gives us our regional kind of diversification. And that helps us on our first point of looking at route preferencing in different regions. And then the most interesting piece here is from line 15 onwards, which is the policy. And this is where we can start to match various policies against the data we're seeing to decide if they're compliant or not. So each policy begins with the root or the prefix, I should say, that we're interested in. And it's evaluated in a top-down approach. So when we see the first match, if there's a match at the top, it will honor that one instead of any that come below it. So in this first case, you can see our match for the default route here in the region of Americas. So we're looking specifically at these routes that appear on routers in the Americas region. We have different types of match criteria you can have. So in this case, it's explicit, but you see down here on some of the others, the match type is any. And this means that we can match explicitly on this exact prefix or on nested or child prefixes. So for the explicit prefix, the prefix we see in our BGP update must match this exactly. So we must see 0000/0. For any type matches, though, we can match either on the prefix exactly, so a /16, or any networks that fall within that boundary. So if we had 192.168.0.0/24, for example, we would see that would be matched by this policy here. So what we're trying to do is build something that was very extensible, very dynamic, and that people can use in their own environments if they want to. And then the interesting piece here is the attributes key, which basically allows us to define one or more BGP attributes that we want to evaluate and the value that we expect them to be. So just as an example, with this default route in Americas, we would expect to see a community value of 100:1 for this specific network. On the right-hand side, this is the script that is doing the actual policy evaluation. So like I mentioned, it's a top-down approach. So when we see the first match, we use that as the criterion. We stop the processing. And basically, the way the system is working is data is being streamed in from the devices. When we see that data come in, we run this evaluate function, which takes the values that we see in that update and compares them against the matched criteria in this YAML file. If the values match exactly, then we classify it as a compliant route. So if the community did match this exactly, then this would be compliant. Whereas if it was something else like 100-:2, or maybe it was missing entirely, we would mark it as non-compliant. And we can do that in real time and present that through some type of visualization tool to be able to allow network engineers and network administrators to see where there might be some kind of issue. So on the next slide here, we can see we played around with a couple of different visualization tools to see what was the best mechanism to kind of get that data out and visualize it. So in the background here, this is a tool we built using a Python Flask app and Plotly as a library. It's just taking the data as we see it from InfluxDB. So I should mention, when we've done that policy evaluation, we actually dump that into a time series database so that we can track the compliance over time. This visualization is taking the data from that database and just visualizing it in a couple of different forms, right? So in this case, we were looking at origin compliance and AS path compliance. Same information is available here in the second screenshot, which is the chronograph screenshot, but probably a little bit neater. You can see on the left here, these are the count of BGP events by the router name. Because our environment was virtualized, it's not really doing anything exciting. So it's relatively static in the number of updates we're receiving at any one time. But on the right-hand side here, you can see, as we were playing around with some of the routing and some of the policies, you can see the count of non-compliances over time. So the higher the bar here, the more non-compliant subnets we see. So we were able to start to visualize this and start to look into it and see how useful this was. And what I can do very quickly, just in case this isn't very clear, is just show a zoomed in version of it in our policy here. We can see from the 18th, so this is from the hackathon yesterday, we were seeing at one point up to 40 of those prefixes were non-compliant at any one time as we were playing around with it. So to summarize, what we were really able to do, we were able to in real time stream telemetry out of our network. This is our network in CML that's running now. We're able to stream data out in real time as the router received the BGP RIB update. We were then able to take a static policy file, which could be developed in the future to be, an API driven or configured through Ansible or something like that. Take that static policy file, match the prefix against a predefined policy, do a real-time evaluation to see if it's compliant or not, and then save that into a time series database so that we can then visualize that in one or several different tools to allow network engineers and network managers to basically see in real time the policy compliance of their network and see if we start to see changes that are maybe not quite right. So if we see, AS origin changes or we see root preference changes, it could be an early sign of something going wrong. So I'm glad to say we got it working. It's running now, or was running yesterday, and we're pretty pleased with it. It was a great event, and that's all we have to show for you. So I'll hand it over to the next presenter. Thank you very much.
So hello everyone. My name is Akash, and I'm a student at the University of Colorado Boulder, and we did a proof of concept tier 2 data center automated deployment and configuration. So our proposal is a fully automated tier 2 data center with automated deployment and monitoring. So why did we do this? From this, we achieve centralized control and monitoring of the network. We get cost effectiveness in terms of reduced operation expenses, one-click configuration and deployment of the whole data center and any new devices. That would save a lot of time and reduction in human configuration errors. So this is a high-level diagram of what we try to do. So we have an administrator who creates Python scripts and features for our front-end web interface, which the operations team or the user can use to interact with the network over the management network. And any data that is fetched from the front-end interface is stored directly to a public cloud, which is in our case Amazon S3 bucket. So this is the topology that we use. So AS100 and AS200 are the two data centers which are on different sites, and AS10 is a tier 1 ISP who provides internet to both of these sites, and we talk from AS100 to AS200 via IPsec tunnel. And in the bottom, you could see there's a customer who could be a tier 3 ISP or directly a customer who just wants to use the internet. And this is the web interfaces screenshot. As you can see, we have lots of features here. We could create configuration files. We could push configuration files to devices. We could monitor the network, and we could also get configuration files for each router for troubleshooting purposes. And lastly, we could store and compare the configurations with what we have as a network source of truth. That is also on Amazon S3. And so this is just a recap of what I said. And the technologies that we are using is basically we are creating Python scripts for all of our automation, and we're using Jinja templates to create configuration files that will be pushed onto the devices. And for communicating with the network devices, we're using Python modules like NetMiko and NAPAM. And for the front end, we're using Flask. We're also using multi-threading for effective and faster deployment of the configurations. So here you can see we have the Jinja templates. On the right, you could see there is a Jinja template for OSPF configuration. On the left, there is a NAT configuration Jinja template. And the user will provide the configuration details on the info file. As you can see on the left, the user provides interfaces and IP addresses that need to be configured. And on the right, you could see the configuration file that is generated from those Jinja templates. So this is a screenshot of running pushing the configuration files from the templates. And here I'd like to show a small video of our code running. So this is the topology, and this is the. As you can see, we do not have any configurations on any of the routers right now. Now we run the script. So as you can see, the files have been created successfully, and successfully loaded into the routers also, as we have pushed the configuration from the web interface. So as you can see on the running config, we can see all the configurations on the devices. And quickly, I would like to show you, we have configured NAT using this method. We've configured IPsec, OSPF, BGP, and 624 tunneling for talking to the other side, which is using IPv6 addresses. And so for monitoring individual devices, we could monitor the interfaces. We could see the neighborship in OSPF and BGP, and we could see running configurations on all the devices. And we can also run any of the show commands for any of the routers to get any extra data that is not provided via the web interface. As you can see, we could just enter the command in here, and then we can see the output. And lastly, I'd like to show how we're comparing the running configuration with golden configurations, which are stored in the network source of truth. So as we didn't change anything, and there was no difference found in the configurations. And this is a screenshot of the files getting stored onto the S3 bucket. And for future enhancement on this project, we plan to implement zero trust provisioning for the management network setup, so that the Python script can directly configure the new devices that come in, and we wouldn't have to manually log in any of the devices to set up anything. Then we would like to do automated device backups, and security is a big aspect. So we'd like to include firewall access lists on the edge of the network, so that nobody can get in. And for redundancy, we can have VRRP running on the edge devices, so that we have increased redundancy and availability and more uptime. So yeah, that was it. And I'd like to switch over to the next host who's going to present.
Hi, I'm Ronnie Mukherjee. I'm pursuing master's at CU Boulder, and I'll be presenting the project, a simple, automated, and easy to deploy SDN solution. First of all, I'd like to give an overview of why SDN is so important. Leveraging SDN, we can reduce a lot of CAPEX and OPEX, our expenses that goes into the network production. So we can move the control away from the devices, and we can use only the applications that are relevant to us by using SDN. And also we can troubleshoot a lot faster, which I have demonstrated in this solution. So the question appears, while having the traditional part of our network, can we still leverage SDN? And the answer to that is yes. You can still have a combination of traditional routing and switching and a branch which is starting with SDN, and check the efficiency of it, and think about moving towards that direction. Only thing that is important in this case is the IP connectivity between the controller, and the SDN environment that we have. This is the network topology that I have used, which I will demonstrate more on the demo video. And the SDN network comes up as any other host. It uses DHCP, so it gets its address from DHCP, and then everything happens. So I have created a Python script which does everything automatically. The routing and anything is not enabled when the host boots up, but everything is done through the Python code. The advantages of the solution that I have proposed in here is that it is easy to deploy using the automated script. Everything is done using one single script. And using SDN gives definitely the advantages that comes with it, like centralized control, global view, and reduction in CapEx and OpEx. And also I have used APIs, which make it a better solution in terms of speed and human reliability. And this can be reused and repurposed for your own usage. I have created a SDN GUI through this project, which shows the graphical statistics of the network real time, and which increases the troubleshooting efficiency in many times. The SDN GUI that we have created in this, that I have created in this, is purpose built for this network, but it can be customized for your own needs. And this gives a real-time stats of the network, and the graphical plots is a great tool to troubleshoot much faster. So this is the topology inside the SDN network. The SDN network that is shown as the cloud has the controller and 4 hosts connecting to the switch, one of which is serving as a web server. And coming to the SDN GUI, I will show these more in details in the demo video. So this is the console logs. One part of the SDN GUI is the console logs, wherein we can constantly monitor different parameters in the network, like TXRX packets, packet into the controller, and firewall rule violation, this kind of things. And this is a picture from the SDN Web GUI, and you can see that we can match on any of the traffic patterns. Like for a switch, we have a particular port, we want to monitor the TXRX on that. And you can have custom traffic definition of your own. You can have firewall rules, you can have web traffic. There are 40 different fields to match on in OpenFlow. And leveraging that, you can create your own custom rules from this Python script. So I would like to touch on the several fields that I have shown in this purpose, one of which is TXRX, and those were tailor-made for the troubleshooting aspects of the networking. So we want to be able to closely monitor switch ports, and having a closer look at the TXRX graphical interface real time would give a much higher chance to troubleshoot any specific issue much faster. And then I have created specific firewall rules to block traffic for a particular host. And we may want to constantly monitor if traffic is coming for the rule that is blocked. And this is refreshed every 5 seconds. So in the real-time graphical data, we can have a clear idea of when the traffic violation is happening. Then there is a web traffic monitor wherein we monitor the web requests. And also I have created a specific match pattern traffic wherein you can say there are 2 important hosts in your network and you want to monitor the traffic between them. So for that, we have created a pattern traffic monitor. And the OpenFlow packaging monitor is the indicator for how many packets are coming from the switch to the SDN controller. So if there is a violation in the count, so for example, the firewall rules, if there is a violation more than, say, 20 number of times, it shoots an email to the administrator. And the tools that I've used for this purpose are GNS3, Cisco. I have used Mininet for my SD network, Rue as my SDN controller. I've used Flash for the web application, and NetConf and NetMigo to access the routers and switches configuration. And I have used Python for the scripting. To conclude, what we have achieved is we have demonstrated that we can easily spin up a SDN network, which can coexist with the traditional routing and switching environment. And we can measure the advantages and the efficiency that we receive from that. And we have created a SDN GUI purpose-built for that network to constantly monitor the network. And the automated deployment of the solution makes it easy to deploy and build in your network. This is the GitHub page that you can find all my codes in. So I'd like to show a short video for the demo that I have created. So this is when the SDN network is getting boot up. The RU controller is running. This is the RU controller running in the background. And now the topology and the GNS tree. So you can see that the SDN network is in a completely different subnet than the SDN controller. So, and there is no routes enabled right now. And so I have used OSPF for the routing. And if you see, none of the routers are currently running OSPF. And the controller cannot be reached from the mainnet, as can be seen here. So now I'm executing the SDN spin-up code from my network admin PC. As can be seen here, the SDN network has taken an IP address just like a DHCP host, and the routing is enabled in the routers along the path. OpenFlow is configured for the OVS, and controller is connected after the configuration is done. So this is how the network is put up, and we can check the Wireshark messages for OpenFlow hello. As can be seen that we are seeing messages from back and forth from the controller to the switch. So this is for the network boot up, and I have another for the GUI as well. So this is when the GUI code is executed, and so as you can see, the GUI is running in here. And I'm pinging the H1 and H2. That is a match traffic pattern that I have, a custom traffic pattern that I've created. And the TXRX also is connecting to the H1. So as expected, the match traffic pattern is increasing, as well as the TXRX for the switch 1 port 1. So as you can see, we are seeing increased curve for match traffic and TXRX. So the next thing that I'm matching on is the firewall. So I'm blocking traffic to H4. So in this case, if this is more than 20, it will shoot an email to the administrator. So as you can see, I'm currently pinging H4, which is not pinging because I have a firewall rule set in there. And as you can see that in the console logs, it shows the firewall rule violation is increasing from 7 to 17. And the curve for firewall traffic monitor is also starting to increase in this. So after the firewall traffic count is more than 20, so as you can see, right now it is 52. So it should send me an email as it does. Yeah, so I have received an email from the firewall count. And now I'll show the web traffic count. So if the web traffic is constantly monitored, I just did a curl for the server, and the web traffic starts increasing as expected. Yeah. So this is how the SDN GUI works. So we have demonstrated that we can achieve the SDN network with ease with the automated deployment, and the SDN GUI gives so much flexibility to troubleshoot and customize. And with that, I would like to conclude. Thank you so much.
Thank you to our presenters and to all of our participants. We're about to begin planning our next hackathon, and we're looking for participants, mentors, and sponsors. To help inform us in our planning, please make sure to fill out your surveys and let us know what you think about the hackathon format and themes. Please be on the lookout for updates, and we can't wait to see you in February.